In this session, we'll be talking about different applications of EFDC Plus and EFDC Explorer in real world. So some of the applications that we'll be talking about, if we have time, are Caloosahatchee estuary that I have shown a couple animations and figures before, Sacramento San Joaquin Delta in Sacramento, California, Little Bow River in Alberta, Sydney Harbour in Australia, Lower Athabasca in Canada again, and Kodiak Airport study. So let's go ahead and take a look at Caloosahatchee estuary. So the objective of this application was to create a EFDC model for TMDL studies, and they would and the client would use this EFDC model as a decision-making tool for managing nutrients in the estuary. Because the big problem in this estuary was they had huge nutrient issues and major algal blooms. So you can see the figure over here with the greenish water. So HSPF is a hydrological model that was used to simulate runoff and pollutant in the river, and the output from HSPF was linked into EFDC model. So this is the figure showing several delineated subbations for HSPF, and this is our study area over here on the Gulf of Mexico. This is our northern boundary, and this small stretch here is our estuary what we will be modeling. And here major roads and areas with triangle are the areas where we will have the measured data. So this is just to show you what were the subbations like when we were doing HSPF modeling. So this is a animation created using EE to show the model domain. This is one way to see it. I mean, this is a smaller estuary, but it's still informative. You can see there are different barriers, or what do you call it, masks that you apply in the model, those black structures. So what masks do is block the flow from this phase to that phase. That means there is no interaction. So there were several masks that were used in EFDC here. You can see the bottom elevation is from -7 to 0.55, and you can see this is deeper in Gulf, and the channel over here on the top where the water is coming in. So this is where the fresh water is coming in. This is salt water here, and again this is salt water coming in from there. This is the figure I showed earlier, the different boundary conditions that we assigned. On the south there is a water surface elevation boundary, and on the north there is again water surface elevation boundary. That's an open boundary. This is on the west direction, this is on the south, and this is again on the west. So this is north, sorry. And the smaller points over here are different point sources that are discharging into the river, into the estuary. So when you try to create a new boundary group, if you right click on being on the boundary condition viewing option, these are the options that you will get, and you can choose to create a new, or if you have multiple boundaries you can just check on add to adjacent. So here the boundary conditions were created based on measured data, HSPF output, and wastewater treatment plant hydrographs. And on the open there were 3 locations where we had open boundaries. This is the figure that you would get if you extract the boundary condition over here, S79. I'm not going over it again. So the model results, after we did the simulation, we'll look at salinity results. So this is so here the salinity is being represented by the contour lines, and different color contours colors are coded here. So the range from 0 to 32, so it's the place where the fresh water is coming in, and this is the location where the salt water is going into the system. So here you have a timing frame for your incoming flow and timing frame for your tides. So you can see when is your flood tide, that's when the water is going into the system. So you can see a nice pulse when the flood tide is coming in, the water is being displaced to the upstream, and when there is ebb tide is flow going out of the system, then the water is moving towards the Gulf. So this is a nice interaction you can create using EE. So this is a so you can see the saltwater waves, and it can reach all the way up to here, but when there is a really high flow, the blue region would be up to these areas. So now we'll create another animation for this center line. We want to create from this point to upstream headwaters. So you can use EE to create a polyline. So what it does is then takes out all the concentrations for those cells and then create a nice layout. So here this is the upstream, this is your downstream at the Gulf, and you can see the concentrations varying at different layers. So this kind of nice gradient is because you have a stratification at the particular layer. So the water is pushing towards the Gulf, and then on the flood tide the water is being pushed from the Gulfs. And also you'll notice that when there is a flood tide, the water surface elevation in the whole system goes up, and when there is the ebb tide, water surface elevation goes down. So this is a nice interaction you can visualize. So this is another animation for DO. It's the same thing. You can see here the bluish color is the maximum value that I assigned for DO. So the water from ocean has a higher DO, and you can see different regions where there will be algal blooms. So when there is algal blooms, there will be more DOs in the system. So here the freshwater coming in, the higher pulse, so you have a lot bigger areas with the blue. So it's a kind of nice. And another thing you notice here, it's calculated at the depth of 1 meter. So EFDC Explorer allows you to extract the values at certain layer or certain depth. So if you're just interested in layer 1, then it can be at different depths for different cells. So if you, for example, in water quality, people usually look at a certain slice. So when you measure the data, you just measure from top to certain values, right? So it's a nice way to look at what's going on that particular depth in the system.
Over there. So I noticed over there that you have a hot spot or the low oxygen spot here.
Mm-hmm.
Land or
There must be some boundary that's coming in the wastewater treatment plant, I think. Yeah, right. So so the system has SODE assigned to different areas. So depending on the vegetation and what kind of water is coming into the system, you would have different DO. So if it has a wastewater treatment plant, the DO would be really small compared to the fresh water coming in. So that might be the cause of that. So this is a similar plot or the animation that we showed before. So the earlier one was for salinity, and this one is for DO. So here the red ones you can see is a lower DO. That means a higher SOD or a higher rooted plant activity or benthic activity going on, and this blue is where you have higher DO coming into the system. So it's a nice interaction, and you can also create these kind of locations where I have specified different locations, so you know exactly at what area what's going on. So if you have area and you have certain landmarks, you want to see what's going on those places, so you can create these. These are called markers. So you have to provide x and this distance and whatever label that you want to use in order to create these. So algal are the same. I'm not going to go over the same graphs again. So what the managers then did after we developed HSPF and EFDC model was they have developed several scenarios. They want to understand what would be the impact if you lower or increase a certain parameter into the system. So then we did a sensitivity study for phosphorus and nitrogen by reducing the phosphorus load to from 50% to 75 and 90%, and then similar thing with the total nitrogen. So when you are doing this kind of sensitivity studies, it's always recommended to change only one parameter at one time, because if you are changing multiple parameters, it's so hard to distinguish which parameter changed that variation into your system. So this is just to give you an overview of what we did and how to use EFDC Explorer to be more insightful for the management purposes. So this is another study area I'll be talking briefly. So you don't have to remember what was in each of those. It's just what were the key features, how EFDC was used to, be more informative. So this is our project location in project location of San Joaquin, Sacramento Delta. So this animation was created using Google Earth. So what we first did was extracted this data for the lake, this study area from EE, and you create a KML file. That's a Google map file, and it's a really huge system. It's like 50 miles on the east-west direction and 70 miles on the north-south direction. So we're dealing with a really huge water body. So you can create these kind of animations to any large water bodies, and you can also have labels right here. It's partly. So all those areas with the values are the river structure. Those were exported from EE and then laid over on the Google Earth. Mm-hmm. And Google Earth allows you, I have another animation for Sydney Harbour that was created strictly from EE, and it's kind of cool to show your boss, look, this is how our study area looks like. And you can also change, for example, this is just the water level here. So if you want to see sediment distribution or whatever parameter you are interested in, you can change this. When you are exporting from EE, you can specify what parameter you want to visualize in Google Earth. Then that's how your color contours will change, and you can display those. So the main project objective was to make a decision-making tool using EFDC Explorer, using EE and EFDC Explorer. So we had to develop a 3D hydrodynamic and sediment transport model, and that was used to gain information about water supply, because there were several areas where there was water supply stations, and they wanted to know about the sediment distribution, deposition, and the scour, what the TSS would look like. And this also depended on ecosystem functions like water quality, and there were several endangered species where they were concerned about. So this is the overall model domain. You can see it's so many networks, and the water in different regions were regulated by pumps. So the pump would be used to regulate water throughout the system. So this is the open boundary over here. So it's connected to the sea, where you have waves coming in, and there are seven pumps that are being used. So to represent pumps in EFDC and EFDC Explorer, what you do is use the withdrawal and return. So pump, what it does is take the water from one location and then take it to another location. So we use withdrawal and return boundary for pumps. And this is Mayor Island. That's where the stage or open boundary was located. And there were 4 locations where the fresh water was coming into the system. And here we specify the tide. So I'll show you some interaction. Oh, sorry. So here we have simulated the salinity into the system. On the top, I have it's hard to tell, but this is a center line where we have extracted the animation. So this is the headwater, so we started from here. So one thing you'll notice is when you are creating these kind of polylines, your starting point would determine the orientation. So if I had this starting point here, my salt water would be fishing here and the fresh water over there, but it doesn't make much difference as long as you can make sense out of here. So you can see again it's similar to the previous animation I showed, where the freshwater and saltwater interaction takes place. And this is the plan view, and this is the slice view. Both of them show the same thing. So here on the plan view, it's showing the depth averaged, because if you want to show all the layers, it would be 10 layers, or if you have to use the difference between particular layers you're interested. So when you're reviewing the overall top view, it's better to see on the depth average point of view. And here you can see each layer, what's happening on each layer. For this model, the TSS was calibrated at several stations. I'll show you station for one result for one station. So this is a Bend station here near the coast, near the coastal boundary, and here the calibration results are plotted for layer 1 and layer 4. So this model had 4 layers in the vertical direction, so the top layer was 4, and overall the calibration was satisfactory. You can see statistics that was created using EE. So we're looking at a huge number of data sets here. We had overall 130,387 points to compare. So these are stations on the left, MAL, these are different locations. And on the bottom there is summary where it says what was the average data, what was the average model data, what was the absolute average error, absolute error. So all of these can be created directly from EE. I think it was exported from EE to Excel to format it better. So anything output from EFDC Explorer, you just copy and paste into Excel, and it will paste in the right places. That's that. So this is another animation to show how the system would behave under low flowing conditions. So the dye was discharged on this branch over here, and then depending on what type of boundary we had this is connected to the fresh water, this is connected to the open boundary. So you can see when the flow coming in from open boundary, the dye concentration is 0 because there is no dye on the open boundary. So the blue concentration will rise on the flood tide, and when it's already stopped, and when it's ebb tide, the higher concentration will be near the mouth because it's going out of the system. So the main purpose is, so from this study, what they found is in the areas where it's connected to the open boundary, the TSS distribution was more controlled by the resuspension from the tides. But on the shallow areas, on these areas, the sediment distribution or sediment impacts were more from the wind effects. So the wind was really critical in these areas. So if we had a model without wind, it would be really hard to diagnose what caused the increase in concentration or the overall distribution in the system. So from this, we just wanted to point out the wind and all the features that you think is necessary. You have to do some kind of sensitivity to understand if you really want to include or not. So now let's move on to another project in Calgary, Alberta. So this is a Little Bow River, and the main project objectives were to create EFDC model in order to calculate water quality parameters for hindcasting and forecasting for future based on different management scenarios. So the scenarios that we were looking at was performance of prediction of water quality loading by running various scenario conditions, like decreasing certain parameters such as phosphorus or nitrogen. So this is the study area, and our study domain will start from here to the downstream over here. So essentially it has Little Bow River on the upstream. Then this is a area which has a reservoir, Twin Valley Reservoir, and it's really deep compared to these areas. And this is a Mosquito Creek coming from this direction, and these two meet over here. And there is a dam that was established after 2004. So for this project we had to do calibration and validation because there was no dam before 2004. So we had to have two different grids in order to do the calibration and validation. So first what we did was we had a SWAT model, hydrological model developed in order to calculate the smaller inflows coming into the system, because there were not much measured data available. You need to have some kind of data to run a model. So the SWAT model, what it does, it gives us flows and concentrations at different locations, and it had so many boundary conditions, so many boundaries that we were including in the model. So here the blue ones are wastewater treatment plants. There were 4 wastewater treatment plants, and there are return flows means coming from different section of river and being dumped into that regions, and these runoff components are from SWAT model. So we use SWAT and then use as input for EFDC model. So on the dam over here, so what we use for the calibration period was we use withdrawal and return. So it's pulling water from the reservoir and then putting water on the downstream. So if you didn't have any downstream section, you could just have outflow, because you have the measured outflow from the dam that you could use for the for your boundary condition. So one thing I want to point out here is we had many issues, challenges, because it's a complex system. There were different kind of water body characteristics. On the upstream it was more like riverine, and near the lake it was more deep, and there was interaction there were some areas where it has more rooted plant and epiphytes, and that would cause more DO consumption. So the challenges we had on this model was we had to use rooted plant and epiphyte, and it had so many parameters that were associated with it. You had to do like number of sensitivity studies to understand which were the key parameters, and a lot of code had to be modified in order to incorporate what we were trying to achieve here. One of the things we worked on was improving the dynamic time stepping on this model, and mass balance of volume balance or mass balance is always important when you are having flow boundaries on top and bottom, because if your flow is not balanced, you are either going to have a sharp decrease in water surface elevation or sharp increase in water surface elevation, depending on whether you have high inflows or low inflows into the system. So it's really critical when you are dealing with this kind of closed system. So we had to do a lot of sensitivity and do a lot of volume based calculations in order to have the exact mass balance into the system. And you can verify that by comparing the water surface elevation at different areas. So if your water surface elevation is kind of low compared to your measure, that means you are missing some flows into the system. And different parameter ranges for RPEM, water quality, ice. There are so many parameters that you can play with, and it's important to get the parameters right, because sometimes different parameter settings can result you to the same results or similar results for 1 year, but if you run for multi-year, then you will discover that that's not the case. That can be a fluke. So it's really important to understand what were the issues. So the calibration was from 2004 to 12, and validation was 1997 to 2003, and 14 water quality variables were simulated. We didn't use all the 21 variables, and 3 different water quality zones were used because they were different in terms of water quality, in terms of depth, in terms of SOD consumption, and rooted plant and epiphyte growth rates. So this is a calibration of calibration at a couple of stations. One, this is the discharge, the blue is the model, and the red is the observed data, and the bottom. So we have the data only in the summer period. So you have observations in the summer. So in the winter they had ice. So this is a vertical profile of temperature at a location in the Little Bow River. This is a dissolved oxygen comparison. So again, we had data in the summer. This kind of low DO might be I think the measured data issue, but we didn't remove anything, just so everything what was available. And another interesting thing to look at long term is how your ice would change with time. So you can see the ice is consistently forming, and these ice formations and ice melt are all dependent on your heat flux components, like what parameter. So it's very important to have accurate temperature parameters. I think I got a Skype message. No. So different parameters were adjusted for organic carbon, nitrogen, and phytoplankton temperature parameters and others. I'm not going to go over each parameter. So I want to show you this animation right here. So this one shows the domain from Twin Valley, starting of the Twin Valley Reservoir to the dam. So before this location we had only one layer, then gradually the layer goes and increasing to 10. So here on the top you can see the gray. This was ice production into the system. So as you can see, as the ice melts, goes and melting, the DO on the top will increase because there will be a reaeration effect. So and within a few days or so, the DO scenario will change. So here the DO was like 4 to 12. I think it's even smaller in some areas, but I clipped from 4 to 12 so you can see the nice change in DO. So on the top, this is the timing frames for the flow coming in. This is the timing frame for the flow going out of the dam. And over here, this is the solar radiation that was specified into the model. I think you don't have the animation, you just have this snapshot on the PowerPoint, but and these are different areas where we know what is the location. This is the TVR, Twin Valley Reservoir, multiple layer start. This is where we started multiple layers. This is the calibration station. This is the location where the Little Bow River and Mosquito Creek meet. So this is a nice interaction to see how how the system would behave with ice on top, because ice on top would limit your reaeration because it wouldn't have any impact. But when there is no ice on the top, you would see reaeration coming from the top and then start mixing to the bottom layers. So that's what I wanted to show in Little Bow. And let's go over to Sydney Harbour. So Sydney Harbour is water body in Australia. So the main objective of this project was to create a real-time model for Sydney Harbour, and they wanted to predict salinity and temperature and build an interface for for the real-time inputting of different variables and then calculating running the model and then displaying the results. There is a little bit time lag because it takes a little bit time to run and output the results, but it's less than a few hours. So the output format for this project was NetCDF data, and this is where we worked on NetCDF, and now NetCDF is part of EFDC Explorer output format, so everyone can use it. And it was used for the web-based portal system and for multiple water management purposes. So what the process that was going on to implement this real-time model was, so you have real-time input, and that real-time input would go into EFDC model. So the real-time input can be rainfall, flows, tidal harmonics, wind, temperature, and humidity. Those are atmospheric parameters, these, and flows. And then the static inputs are the modal bathymetry and other parameters that wouldn't change with time. And after we have all the input files that is necessary to run, then the model EFDC model was run, and the simulation was done with the Red Hat Linux platform, and the output of the from this Red Hat Linux was created in the format of NetCDF. Then that NetCDF was used to create the visualizations, which would give water levels, velocities, salinity, temperature, and bed shear stress. Again, the boundary conditions, they had open boundaries and flow boundaries. I'll show you what were the boundary locations. So they were not interested in the atmospheric data for that particular version when we worked, but they had wind and wind speed. This is the bathymetry data for the Sydney Harbour. This is the scale is 2 kilometers, and the bathymetry range from -42 to 2.2. And this I have created a center line here so I could show you the vertical slicing animation later, and these are different locations that will be used on the animation. This is the grid that was used before. At that time, I think they have expanded the grid now from this location to somewhere offshore. I think this model used Cartesian grid, and the number of horizontal grids were 12,644. Now I'll show you the animation of the salinity, depth average salinity. So in this animation, these are two major rivers that are flowing into the system, and I have also shown the velocity directions into the animation, so you can see how the water is coming in or which direction water is flowing in. So when there is a ebb tide, as usual, you can see the velocities moving into the system, and on the, flood tide velocities coming into the system and ebb tide going out. But as you can see on here, the para boundary, you can see the hydrograph is rising. That means high flow is going to be introduced into the system. So this line here means what was the value of the discharge at that particular time. So as this time changes, the location of this timing frame is also changing, so you know what was the overall flow distribution into the system. Now as you can see, the flow is moving, higher flow is coming into the system. It's all blue. That means the fresh water is coming into the system, and same thing over here, and until it goes to over here, then the salt water will dominate, and then it will push the water towards upstream. So just wanted to show you the high flow interaction with the salt water interaction. And velocities, you can control at what frequency or at what I&J index you want to display the velocity in EFDC Explorer. This is the animation showing the salinity salt animation. Again, it's nothing fancy, similar looking plots, that animation that we saw in different projects, salt. And so the takeaway from this animation is just showing you the way to create timing frames, the upstream and downstream, and including these markers so you can tell what's going on at what location. And in these kind of animations, it's best to make your scales constant. So if you don't do it, make it constant by default, I think it will change at each time step, so it's hard to tell whether it's really increasing or not. So just make sure to have your scales right or not changing. And here you'll notice that and I have also displayed wind. So here the wind was scaled for a 5 meter per second velocity, and then each time the wind will change depending on which direction it is flowing to. So this is the animation I was talking about before. This was created from EFDC Explorer. Let's see if it plays. So this is a Sydney Harbour 3D flyover. So this is the topographical file that you can import into EE, and then in 3D view, and then you go and create a flight options, and you can see a nice looking animation showing different areas of your study area. So here they have included the landmarks, breeze, I think that's Opera House. Yeah, so you can include these collada files and you can include into your model. So yeah, and I have included the link on the bottom, you can look into it. I think there are collada files that are available for download in our website, so you can use into your model. So you can choose the flight animation path. You can go at different depths. You can go to the bottom and then come on the top, and you can specify what elevation you want to look into these areas. Yeah, just wanted to point out you can create really cool animations from EE. So before I showed you the animation that was created from Google Earth using the KML created from EE, and this is directly from EE. Feel free to choose which one you like. I think we'll conclude our session for this at this point.